Is it possible for an electric field intensity E to exist in a source-free dielectric medium? Because the issue here is that for any field to exist, it needs to satisfy all of Maxwell's equations. Before we answer that question, let's first of all look closely at what is inside this box here. A source-free medium is one where the volume-free charge densities are equal to 0. In other words, our rho V is equal to 0. Secondly, there is no conduction current density. In other words, our J is equal to 0. Now, when we look at the electric field intensity itself, it's only got one component, which is in the x direction. Secondly, it's a time-varying electric field intensity. And whenever we have a time-varying electric field intensity, there is always a time-varying magnetic flux density associated with it. So in this video, what we're going to do is, first of all, to find the B field associated with this field. Then we will find the H field, which is the magnetic field intensity. Then we will find the D field, which is the electric flux density, and finally the J. But we have just discovered our J is equal to 0. Finally, we will then go ahead and prove each one of these statements here. First of all, that our divergence of B is equal to 0. The divergence of D is equal to 0, because remember we found rho V is equal to 0. And finally, the curl of H should give us that, which is partial D, partial T. Remember, our J is equal to 0. So, let's use our first equation to find our B. Now, it says here, let me use the black. It says here, curl E is equal to minus partial B, partial T. Now, because our E has only got one component in the x direction, our curl of E is going to give us a C beta sine of omega t minus beta z along the y direction. Now this is curl of E, but curl of E is equal to minus partial B, partial T. Therefore we can write partial B, partial T is equal to minus that, which is minus C beta sine of omega t minus beta z along the y direction. This is minus because this was positive and this is negative, so we took the negative sign to the other side. So partial B, partial T is equal to that. Now, if partial B, partial T is equal to that, B itself is when we integrate this expression here. So therefore, our B is equal to C beta over omega cosine of omega t minus beta z along the y direction. To create space, let me clear this one here and write our expression for B in its place. So we can write here, maybe we should emphasize this in red. So B is equal to C beta over omega sine of omega t minus beta z along the y direction. I hope you can see my red clearly there. So let's create space here and do our next part. Now we are going to find our H field. Now H, of course, we know that our H, we know B is equal to mu H, where mu, of course, is the permeability of the medium. So therefore, this implies that our H is equal to B over mu. So all we have to do now is to divide this by mu. So our H, the H field is equal to C beta over mu omega sine of omega t minus beta z along the y direction. So I can just clear some stuff here and put our H field. Put our H field here. Before, let's put it in red. So that's going to give us our H is equal to C beta over mu omega sine of omega t minus beta z along the y direction. Our next assignment now is to find the D field. Let's find our D field, the electric flux density. Now, the electric flux density, we know that D is equal to epsilon E, where epsilon is the permeativity of this medium here. So therefore, our D is equal to epsilon, we multiply this by epsilon, C cosine of omega t minus beta z a x. So let's just clear this and put our expression in its place. It's getting in the way. Okay, so back to red now. Our D field, D is equal to epsilon C cosine of omega t minus beta z along the x direction. So we've got our B, we've got our H, we've got our D, our J, we have discovered is equal to 0. So let's just book it there to keep us in remembrance. So we're going to write J is equal to Z. Now, what is left now? We have found all the fields associated with this field here. Our next assignment now is to prove this and that and that. Now, first of all, our divergence of B. Now, let me clear this first. What is the divergence of B? Well, the divergence of B, which is that, is equal to partial B along the x direction, partial x, plus partial B along the y direction, partial y, plus partial B along the z direction, partial z. Now, if you look at our B here, where's our B? It's this one here. It's along the y direction. So there's nothing here, there's nothing there. We are only interested in this part here. But when you look at B, it's not a function of y. It's in the y direction, yes, but it's not a function of y. So the divergence, partial B, y, partial y, is actually equal to z. So we have proved this one here. The divergence must be equal to z. And we have discovered here the divergence of our B is equal to z. Our second part is going to be this part here. Partial the divergence of D, the divergence of D is equal to partial D along the x direction, partial D, partial x plus partial D along the y direction, partial x plus partial D along the z direction, partial z. Oh, so this is supposed to be y, sorry. Okay, now look at D. D is along the x direction. So this does not exist. This does not exist. So this does not exist. This does not exist. We are only interested in that part. But when you look at D, the D field, it's not a function of x. So this is equal to 0. So therefore, we have proved that the divergence of our field is equal to 0. Lastly, curl of H. The last part that we want to prove is curl of H. Right. So curl of H, our curl of H, it says curl of H is equal to J plus partial D partial T. But we saw earlier that J is equal to 0. So therefore, all we have is partial H is equal to, curl of H is equal to partial D partial T. First of all, what is partial D partial T? Well, there is our D field. So partial D partial T is equal to that minus there. So it's going to be minus epsilon omega C sine of omega T minus beta Z along the x direction. Let me see if I can write it somewhere. Okay, but it's fine. Now, what about curl of H? Because remember, this must be equal to that. So let's find curl of H. Let me just put this inside the box. Keep it safe, So partial curl of H is going to be where's my curl of H? It's going to be minus C beta squared over mu omega sine of omega T minus beta Z along the x direction. Because remember, our H field is only in the y direction. So it will give us this as the curl. Now, if this is going to be equal to that, remember this part is the same. So that means the coefficient of this term, which is that one there, must be equal to the coefficient of this term here on the other side. So we can write, let me clear this here. So we can safely write that our minus epsilon omega C is equal to minus C beta squared over mu omega. The minus signs obviously cancel out, don't they? And the C here cancels with the C there. So we can leave our beta squared on one side to get this implies beta squared, so is equal to epsilon omega squared mu. So our beta is equal to plus or minus, we take square root both sides, omega square root of epsilon mu. So for this field to exist, we found that it satisfied divergence of B is 0. It's satisfied divergence of D is 0. Now, for it to exist, here are the conditions. The condition is that this beta here must be equal to plus or minus omega square root of epsilon mu. This is the condition that is required for this field to exist. Remember, our question was, under what circumstances would this field exist in a source-free dielectric medium? If this condition is satisfied, this field is possible. If you are happy with our presentation, please subscribe, like, and share. Till we see you next time, take care.